Good morning. It's a pleasure for me to present Malin Stanescu. Malin works in the Astronomical Institute of the Romanian Academy in a project with Marcel Popescu and also with Ovidiu Paduescu. This is a group we have a very close cooperation since a year and very productive one, I should say. And Malin is a software engineer, but very interested in astronomy.
Yeah.
Since long, and he's working in this ParaSOL project. That it is, as you will see, is a very interesting new methodology to detect asteroids, in particular near asteroid that moves very fast. So I let him start and explain you what's going on with this field. Thank you, Malin.
Thank you. So today I'm going to talk to you about detecting asteroids fainter than the limiting magnitude of a telescope through the use of synthetic tracking, and by using our software, doing so in real time. So first, who are we? We are the ParaSOL team, part of the Euronear research network that aims to discover and recover near-Earth asteroids. We have collaborators in many European countries as well as Chile. Some of them are professionals, some of them are amateurs. And it is actually through one of these professional amateur collaborations that the umbrella moving object processing system was developed. And later it morphed into an entire software suite for detecting asteroids. Through a government grant, we have managed to get this ParaSOL project running to extend the software suite with a module for doing synthetic tracking. It's this SDU, as well as a pipeline to take the raw images from the telescope and make them available in a form that's usable for detection algorithms such as STU or Blink. This is the IPP pipeline. Finally, to show the results of all these pipelines, we have a web interface that we call Webrella. So, mention detecting asteroids. Actually, we're not detecting just asteroids. It's pretty much any object in the sky that moves on a nightly basis. So we're not talking about star movement. We're talking about things that are within the solar system and sometimes also some interstellar visitors. They're really rare, but they sometimes do show up. So what does an asteroid look like? What is it like? So we all know, maybe it's like a space rock between Mars and Jupiter. And sometimes they get knocked off towards Earth. Well, not quite. So on your left, you're going to see, on your right, you're going to see Bennu, which is actually a neighbor of us. And it's an asteroid that's about 500 meters large. This is an image taken actually from very close. You're not going to see them this clear from the Earth. They just look like a point source. Even like the biggest ones, you can't quite see them like this, just as a note. So this one is actually not monolith. Yeah, it's not big space rock. It's actually composed of many small pebbles, which is why we call them rubble piles. And I mentioned it is close to Earth. This is what we call a near-Earth asteroid. So why do we care so much about asteroids? First of all, they are unaffected by the geology that you see on major planets. Especially on ours, where you have all this weather and bioorganisms that change the structure. So if we can study these asteroids, we can tell about what was the solar system at the beginning like. Also, another important point is that some of them are pretty easy to get to. This is also how we can actually get these kind of images. Some of them are actually more easier to reach than our own moon. And there is also part about planetary defense. So we don't expect an asteroid to be a serious threat for humanity, but they can be rather annoying, as we've seen, for example, with the Chelyabinsk bolide in Russia about 15 years ago. It's actually injured quite a few people from the shockwave that broke the glass of windows. and it also made a pretty big media frenzy. So we kind of want to keep an eye on them. Okay, so how do we detect them? Well, we do this optically with just plain mirrors and cameras. We do so because the atmosphere is transparent, very well transparent in the optical region, and the sun has an emission peak in the optical region. And because the asteroids just reflect light, it is so much easier to do it this way than any other method. In terms of what we actually see on the sky, they usually move between 1 arcsecond per hour for like very distant objects. We're thinking here trans-Neptunians, Kuiper belts, and all the way to 100 or more than 100 arcseconds per minute for objects that are really close to Earth. Some of them pass closer than Earth's own moon. And for those, yeah, the speeds are really great. If we want to detect new objects, we typically want to go fainter than magnitude 21. So if we're looking at objects that are magnitude 20 or less, they're either objects that are very small and pass close to Earth now since a long time ago. So we haven't seen them around Earth for a really long time, or they have already been detected by the big surveys. And as an example of the instrumentation that we are using, this is the Isaac Newton telescope with the wide field camera mounted on. This setup has a 2.5 meter mirror, and the wide field camera is actually 4 CCDs of slightly more than 8 megapixels. It's actually about 9, and it covers about 0.3 square degrees of the sky. We typically take exposures of 30 seconds because we want to use this with synthetic tracking, and we'll get to why it's this short exposure time in just a short moment. So what do we do with the data that we receive from the sensor? The classical detection method for this is called blink. You basically take a few exposures, you alternate between them, and you scan the image for them. And this is basically the manual process. But of course, we're in the computer age, so you can do this automatically. Computers don't, scan the image and alternate between images. They don't blink, but they actually extract the sources and pair them. So they look at all the objects that are in the image by trying to extract the parts that are more luminous, and they're trying to see if they can fit an orbit to those sources that do not appear in the same place on several images. Now, to be able to detect these faint asteroids that we're interested in, we're going to have to battle this signal to noise ratio. So you really want to have a good signal and try to avoid the noise so that you can actually separate the asteroids from the background. Of course, all this is quite probabilistic, and this is why this method is actually more signal analysis than, I don't know, classical computer vision or any other related astronomy stuff. It is actually signal processing. So if we're thinking about this probabilistically, what would this look like? So we have a distribution from the sky, noise distribution from the sky, and also distribution of the photons coming in from the object. Both of these are Poisson. For the object, it's pretty easy. We just get photons, and those obey a Poisson distribution at the sensor. And this is actually quite similar for the atmosphere because it glows. So it has about a magnitude of 22 per arcsecond, and it emits light. So what you want to do is to detect the light on top of that. So if this is your bottom zero signal on your sensor, then this is going to be the atmosphere, and your object is going to be around here actually. And to be able to tell that there is an object here, you need to make sure that the object is actually above the noise of this distribution. So for example, if you want an object at 3 sigma, you're going to have to identify this object above that noise level. And at 3 sigma, you're actually going to have, for a multi-megapixel sensor, thousands of pixels just by random noise that are going to be brighter than that. All right. So how do you get more signal to noise ratio? The usual way to do this is to just increase the mirror size. So we're having here, for example, the Pan-STARRS, which has 2 telescopes, about 1.8 meter mirror. And there is a new project to build a bigger one, LSST, as it's now known as the Vera C. Rubin Observatory, which is planned to have an 8-meter mirror. Now, the thing with these mirrors is that they're quite expensive. So Pan-STARRS actually gets funding directly from the government through Congress-approved budget. And the LSST actually is even worse in the sense that not only does it get funding from the government, but it also has some massive private funding to be able to finance this telescope. So the costs are estimated at about $700 million for that. Well, because they're so expensive it's so expensive to get a big mirror, how can we keep the costs low? So can we keep the mirror small? So the signal to noise ratio formula, it's gonna be proportional to the surface of your mirror and the time used to integrate. So if you want to keep your mirror small, then you're gonna have to integrate over long times. But in that case, you have a bit of a problem in that your asteroid is gonna move against the sky background, so it's gonna leave a trail on the image. And if it's gonna leave a trail, you're gonna get noise under the trail. And this is your big problem. Yeah, you want to keep the signal, but get rid of the noise as much as possible. And so when you have this trail with a PSF, it's gonna cover an area that's proportional to the length of the trail. So if you want to get better noise properties, you're gonna have to take shorter exposures and try to co-add them. And if it's a known asteroid, this is pretty easy. You just add them along the trajectory of the asteroid. But what do you do if you don't know the trajectory? So as I mentioned, we're trying to discover new asteroids. Turns out you can actually do this. This is a procedure called synthetic tracking. And it's actually pretty simple in its idea. You just try every possible motion vector. Of course, this allows you to use smaller mirrors and do so by using longer integration time. But the trade-off is that you're going to need a lot more computational power. And this used to be really slow. You can see some old papers, they're just using it for like one-off projects, let's say. But with modern computers, you can start thinking about using it actually in surveys. And there's been big gains in computing power and especially in accelerator hardware. So if normal CPUs gain about 10% per year, the GPUs, for example, one type of accelerators, are gaining almost, they're basically doubling their performance every release cycle, so about 2 or 3 years. And you're going to start seeing now examples of synthetic tracking. This is taken with the INT and wide field camera that I just shown you. 12 images, 30 seconds exposure, 30 seconds readout. Yeah, and this is actually close to what you can do with Blink. But with synthetic tracking, you can see this object much, much better. Same as with these new slides. Yeah, as I mentioned, you're going to see a few more of these examples. Now, why is it so hard to do synthetic tracking? Well, it turns out if you try to check all possible motion vectors, you're going to have to test trillions of hypotheses. So if you have maybe 100 vectors per axis, then you're going to get up to 10,000 motion vectors to check. So it's 100 square. And you can maybe get even a bit bigger, 1,000 pixels. If you want a faster asteroid, that's going to be 1 million vectors to check. And that's for every pixel. Yeah. So you're easily getting into the trillions because you have multi-megapixel cameras and maybe even more than trillions, tens of trillions. But this is not the whole story. So you have to co-add the images for each one of these hypotheses. So you're going to have to read from memory the pixel values on each hypothesis for every image it intersects. So you're going to be looking at hundreds of trillions to even quadrillions of memory reads, for just doing the synthetic tracking on one field. And it gets even worse. So not only do you need to read from memory, if you're going to have a lot of images, you need to get rid of the outliers. So you're going to need to have something like a median coalition. And that's very expensive because it needs sorting, and sorting is really expensive. So if you go out with something like mean, this is pretty easy. You have, because addition is associative. So you can just keep in an accumulator your current mean, or the sum you can divide afterwards by the number of images, and you just add the pixel values. But for median, you can't do that. You need to store the list of all values and shuffle them around. And that's way more expensive. And if median is expensive, then you need to think about how you detect them. And after you do detections, you also need to filter the remaining detections. And this all gets even more computationally expensive. So can we make it fast? It turns out that yes, we can. So the most important thing to start with is to try to move the expensive operations at the end of your pipeline when you've already filtered some of your detections, and you can run these expensive operations on pure objects. So the idea would be to have initially a very quick first scan of the whole image, get some ideas of where all the possible objects are, and after that, start removing objects with increasingly more expensive filters, but that are also more powerful and can reject better the false positives. Now, even if you do this, you're still gonna have the first part that you have to scan the whole image. That doesn't go away. You still have to check all those hypotheses. And the good part is that you have to do this on every pixel and for every motion vector, and this is parallel. You can make it massively parallel. You can just run the same procedure for every pixel, at least if it's a simple method. If you're gonna do a very complex detection method, that might not work. But for simple methods, you can just parallelize it over all the pixels and do it in parallel. And there is one more thing you might want to consider, and that if you want to get rid of as much false positives from the outset, you may want to still keep using something like a median, but not do sorting, because as I mentioned, sorting is expensive. So if we can do this kind of median without sorting, that would be perfect. And finally, after you've considered all of these, you can start thinking about how to use your hardware efficiently, how to make the best use of how computers work to make your software even faster. And yeah, how do you actually do this part, and how do you use the accelerators to make this massive parallel search efficient? So accelerators differ from CPUs in that they are massively parallel. Like, they're designed to be this massive parallel thing. They don't accelerate your normal single-threaded code. So, for example, when you're writing your usual Python code, you just do instructions one after another sequentially. That's a single thread. In these accelerators, you just do your operations on all the data at the same time. So you actually see here an image of one core of an accelerator. An accelerator typically has tens to hundreds of these cores, and each one has tons of what's called vector processors. You can see them in red. Each one of those can do an operation on one piece of data, and then you can do it over large amounts of data in parallel. And you no longer need to bother with keeping track of various operations as you would do in single-threaded mode to improve the speed of just one execution flow. And instead, you can dedicate all of that just to doing brute force computations. Moreover, it's not that you're going to get a lot more accelerators per square millimeter of silicon space. You're going to get more silicon with accelerators. So if you're going to look at a modern GPU card, it actually has more die area than a CPU. and it also has more power budget. So while a CPU uses between 50 and 100 watts, these accelerators can go to 300 watts, 500 watts, and so on. And you're also going to get more bandwidth to the memory. So modern CPUs are usually a few tens of gigabytes per second of bandwidth to RAM. Maybe with these new DDR5 memories at very high frequencies, they can reach maybe 100 gigabytes per second, but that's it. For GPUs, they start at hundreds of gigabytes per second. And if you're going to look at the top GPUs available currently on the market for consumers, I'm not talking about the data center ones, which are in different league, you're going to see bandwidths of even up to 1 terabyte per second or a bit more. And the final benefit of this is a parallel programming model. So to actually make use of this, you're going to need something we call a software development kit, a compiler and some tools to get your software on the accelerator. We're using OpenCL. Another popular one is CUDA. So in these accelerator programming modules, they're designed to make you write your code for a single thread. So if you're looking back at, these vector processors, you're actually writing your code as if it's running on each one of those small vector processors, and then it's taking care of parallelizing them across the accelerator by itself. You don't need to bother with that. So this makes it very easy for you to write parallel code. And if you, for example, consider the memory hierarchy, so the idea is to use as much your fastest memory, which is closest to the execution units, and try to avoid going to the bigger memories, which are slower, then you can actually get a pretty decent speed up. And this is true not only for the accelerators, but also for regular programs you'd write for the CPU and so on. So even, for example, if you're just doing some image processing in Python or Bash, it's much faster to take the same image and go with it through multiple steps than taking all the images, going with them through one step, saving them to disk, and then reading them back again from disk, doing another process, and so on. There is one more thing you may want to consider when writing GPU code, which is branchless code, in that branches are quite expensive on CPUs, but especially so on accelerators. So for example, if you have a piece of code that computes your maximum value between two numbers, usually you would write something like if value A is smaller than value B, then you're gonna output value B, and in the other case, you're gonna output value A. So you can actually do something pretty neat due to how the hardware works. So when you're doing this comparison, A is smaller than B, it's actually gonna output to you 0 or 1. And you can use this, so you can return the comparison. So this 0 or 1 times A plus 1 minus the comparison times B. And this is just gonna give you, just by multiplications, the maximum value. And because there's no branches, it actually goes much faster. And if you take this into account, you can actually write some pretty efficient code for the accelerators. There's a bit more to consider usually, but if you just want to start, because it's actually quite easy, with these, you can actually start writing code. So the thing is, the hardest part of writing code for the GPU is doing the setup, getting the SDK and sending data to the GPU and back, because on the GPU itself, this is just plain C code and you can write it pretty easily. So how does this all work with Stu? We have, as mentioned, started with this hypothesis rejection design. This is absolutely necessary if you want to get a good performance. And not only that, we are actually doing a bit of image processing in Stu. We're not doing it just in IPP, so that we can get rid of variations in the images due to night changes. For example, if some clouds come over or something similar, where the level itself of the image may change. And that way, our algorithm can be really simple. It doesn't need to bother with all these special cases. It can just go through the data very quickly. And actually, the part that does this, it's not mean or median or anything like that. It's something we call a detection scoring method. It actually does something similar to mean and median at the same time. And it benefits from the outlier rejection properties of median, while still being associative. So remember when I said that we can use some accumulators to just add data as we go through the pixels? Yeah, we actually do this for our detection method. And this is why it's so fast on the GPU. Now, the output from the GPU is going to be one motion vector per pixel if there is a detection there. So usually when you have a detection, you're going to have multiple pixels that belong to the same detection. So one thing you want to do after this stage is to cluster them together so that you would get just one object that you can process later on. This is the clustering part. And with this object, you can start trying to see which one of these pixels is the center of detection. Yeah, what's the best motion vector and center of the object to define your detection. And this is the refinement stage, the third stage in our pipeline. And with this, once you know how your object moves, then you can actually measure it. So you can send something to MPC and also filter the false positives. Yeah, you need to know something about your object if you want to remove the false positives. Also, we have a pretty efficient design on the GPU. We're using caches a lot. We are going faster than the bandwidth to our memory is. So for example, on the cards that we're using, we have 500 gigabytes per second to memory, and we can reach between 1.6 trillion to 2.4 trillion operations per second. So it's much faster than we're actually accessing the memory. That's because we're using the cache. And this latter 2.4 trillion figure is obtained thanks to some modern AI acceleration instructions that are available on modern GPUs. Our software is also quite portable, so you can use it on Windows, Linux, and thanks to doing it in OpenCL, which is portable across vendors, you can use AMD, NVIDIA, or Intel cards. We've tested on all of these. Now, how fast is this? We've talked about, that we've made it so efficient. So it turns out our software can actually do this in real time. Yeah, so doing it faster than data acquisition. This is our card that we're typically using, this Radeon RX 6800 XT. And for the wide field camera, we have these set up with 4 9 megapixels sensors. And by taking those 12 images at 30 seconds exposure plus 30 seconds readout, we're gonna acquire these images over a period of 12 minutes. And the time to analyze this data, it's gonna be 26 seconds per CCD, so 2 minutes in total. With the actual brute force scan, which is the one that usually is considered the expensive part of synthetic tracking, just 2 seconds. And this is at something we call full granularity. I'll get to it in a moment. For the TATS telescope, the TAT South, which has an 80 megapixel CCD, we've taken 20 images at roughly 1.5 minutes cadence. The thing is, this telescope doesn't take them very regularly. It has a bit of a variation in the time between exposures. And yeah, the total acquisition time is roughly around 30 minutes. And by testing this with a 15 arcsec per minute search cone, we have reached a runtime of 7 minutes. Yeah. And the actual synthetic tracking part is 2.5 minutes. Much bigger CCD, a lot bigger search space, still order of minutes and faster than acquisition time. Now, as I mentioned, this was at full granularity. So what's granularity? When you're starting from the origin of your motion vector and you're going on your motion vector intersecting the various images, you're gonna get to a point where it's like the furthest image from the origin of your motion vector. And we compute granularity. We say this granularity to be in pixels on the furthest image. So 1 pixel on the furthest image is, if you've ever used TICO, if you're working this asteroid detection and you know the TICO software, this is 100% in TICO. And you can go below this. TICO, for example, recommends between 25 and 30%, which it means for us about 2 pixels. So if you're looking at this same TATS dataset, we can detect main belt asteroids by decreasing the granularity and turning on thirding, which is basically just checking the inner vector first and inner images first, because after we've gone through a few images, we can tell whether that vector is probably going to lead to a detection, or if it's, you just see that it's negative, let's say in its core, and it should be quite high positive, you can just drop it. Yeah, not bother checking the other images. It's not worth it. And with these, we can actually get for these main belts at 52 milliseconds. Yeah. This is faster than you can actually blink. So this used to be a joke of mine. Used to call this presentation beginning it with blink and you miss it. So making a bit fun on the blink method. Now, at these 52 milliseconds, this is practically instant for the slower moving objects. So if you're trying to detect main bolters, yeah, you just use this. It is instant. Like you just type the command, it pops up. The only thing that prevents you from getting this kind of instant feedback was that if we go back here, you see that the synthetic tracking search is only 2 seconds, for example, for NT, while the whole procedure takes 26 seconds. That's because there's still quite a bit of cost in doing the image processing and post-filtering, which is also a bit image processing in itself. So if you get this on the GPU, the speed up is much greater. So for example, I saw this on the INT, because this is something we're currently doing. It's roughly around 2 or 3 seconds per CCD. So you're gonna look at probably 5 seconds for each CCD of INT with the newer software. As examples of what we have managed to detect with this, so on the left here, you have the 2024 CW2, which we typically use to demonstrate the search cone of STU, because this was detected at 9.5 arcseconds per minute. This is a near-Earth asteroid. And the image that you're seeing here is actually what our collaborator, Lucian Cuvelavo, saw when he first saw this object. So basically the first time anyone on Earth has seen this object through a telescope. And the nice thing about this, and yeah, this is a pretty high search speed for synthetic tracking, is that we have reduced the entire data for the night. And we had 2 more detections like this reported within 24 hours to the MPC. So by the time it was the next night, we could already start fresh. And another interesting detection in a different way is this 2023 DZ2, which actually moved slightly slower. I think it was 6 arcseconds per minute. I might be remembering wrong though. And this one turned out to be a virtual impactor. So after more observations of it were taken, we have noticed that its orbit had a pretty big probability of intersecting Earth. Pretty big here means 0.23%, which actually put it on something called Torino scale 1. Yeah, 0.23, as I mentioned, there is very little chance of asteroids actually hitting Earth. But yeah, we're actually monitoring this, yeah, just in case something does happen. Okay, and this is with a slightly different output, also from STU, but we rerun it with different settings so it looks better, for the press release. Now, for the interface, this is what WebRela looks like. So you can see there on the right, that's the same DZ2, how it looks like in the interface. Why do we do this kind of web interface? So it turned out that reducers, or at least some of them, weren't very keen on running very computationally expensive programs on their computers. And this is especially true for synthetic tracking, which needs powerful GPU, at least to get really high search cones. So it would be best to just put it on a server. Now, there is actually an additional benefit that we saw from the first edition of WebRela. This is the second one, in that when you have this on web, you can easily share links to the detections, and then everybody can pitch in. So if it's an interesting object, maybe it's something that's moving very fast, you can just send it to your collaborator and they can take a look immediately and start preparing to send it to the MPC. You don't need to wait to validate all the data, and after that, then, and trying to point somebody to this detection. And there are more benefits to using WebRela for this validation. So this is not your everyday website, and it's not like, I don't know, the Times on web. We have optimized it to be very effective at validating. The idea was we took and we wrote the code of Umbrella manually in HTML and CSS so that it would be very responsive. It also has a bit of JavaScript just for some interactive parts, which I'm going to tell you about in a second. But otherwise, it's HTML and CSS. It loads instantly. So you can navigate there very easily. You can load a page and it will just load instantly. You don't need to wait for anything. And the second part of this is the keyboard navigation. So you can actually, and this is what we need the JavaScript for. You can navigate between all the detections through the WASD keys, and you can actually switch the representation of the image. So I showed you here two different types of images, one with the stars masked and one without the stars masked. And this is actually just a mean coaddition. You can switch between these types of representations from the keyboard as well with Q&E, and you can also copy, for example, the MPC report, so we can check it, let's say, very quickly against some other database with the C key and so on. And the other benefit of it is that you have the information immediately available. So everything that you want to know about the detection, it's going to be there in the left side. Now, with all this, we have managed to show that it is possible to do real-time synthetic tracking, and doing it pretty cheap, yeah, with some cards that are not very expensive. So that 6800 XT, when it was new, it was about 600 euros, maybe 700 euros. Now you can get it secondhand for like 400 euros. So this is actually available for everyone. You don't need some kind of big, expensive HPC cluster. We have done this test on several telescopes, Telescopio Carlos Sánchez, the Isaac Newton telescope, T025, which is a 25 centimeter telescope at IERA, we're using it as our home telescope to do quick experiments. Also, SAR, ACAS, NT8S from Chile. And we've done this with 100,000 images, mostly TCS, but also in the thousands to tens of thousands for the others too. What we've discovered from this is that the detection rate depends a lot on the quality of your pre-processing, so the equivalent of IPP or IPP itself. For example, on the 25 centimeter T025, we haven't missed any detection on the part that was showing good images. It's not like all of them are good, but at least on the images that are good, we don't miss asteroids. And for all these telescopes, we have managed in the end to get an end-to-end pipeline, so from raw images to the detections. Unfortunately, that took a lot of our time because every telescope really has a different output, and you need to do various things to the headers of the images and so on to be able to get something out of it. And the thing is, for all these telescopes, or almost all of these telescopes, we have done this as real-time surveys. Like we literally took images and reduced them afterwards, like in the following day, and sent data to MPC. So we've simulated these kind of real-time survey conditions. And what we noticed is that the limits to getting these data as fast as possible to MPC is one, the transfer bandwidth from the observatory, and second, the human factor, in the sense that humans usually don't start reducing as soon as the data is available. You need quite a few people to do that. And then you get a bit of a delay by introducing humans in the chain. So from all these experiments that we've done, what are the limitations of synthetic tracking? So as a method itself, one of the big problems it has is that it tends to lead itself to the data dredging pitfalls. So the idea here is that you're trying lots of hypotheses, and what's going to come out of your pipeline, it's just going to be the good ones, yeah? So for example, if you have some random noise that lines up, you're just going to see that lined up randomness. You're not going to see all the other things that didn't pass through the pipeline. And this gets even worse the more filters you add. So if you add filters that match the expectations of human validators, then you're just gonna get rid of the false positives that would be obvious to the human validators, and you end up with false positives that look like real ones, even for human validators. So this all leads to not being able to tell very well which parts are, like which detections are the good ones and which ones aren't actually. Another limitation is whether you can actually observe the sky for long enough. It's this diurnal cycle. So as the sky moves around, you only have a limited window to observe a certain portion of the sky. And this actually matters a lot for the near-Earth asteroids, especially the ones that you want to detect close to the orbit of Earth. So if you're pointing at night closer to zenith, you're actually going to detect objects that are having an orbit exceeding that of Earth. If you want to go towards the interior of the Earth's orbit, you're going to have to observe at low elevations, and you might not have a lot of time to do that. Then there are the aspects of the processing and electronics. So one is the size of the data cube that you're analyzing, because you only have so much memory, especially on the accelerator part. Memory on servers is usually better, but the accelerators themselves only have, I don't know, 10 gigabytes, 16 gigabytes, maybe 20 or 30 with the neural cards. So the amount of image data that you can process for synthetic tracking is quite limited at the moment. Maybe will improve in the future. And another one is the sensor cost. So if you're making your mirrors smaller and you need to observe a large area of the sky, then you're going to still need a high resolution sensor to cover the entire area. But if you're trying to multiply this so that you can get the equivalent of a large telescope, then you're going to have to spend a lot on the sensor. So for the famous RASA 11-inch plus the IMX 455, either QHI or ASI or whatever, you're going to see that your sensor is going to cost a lot more than the telescope and even telescope plus mount. Now, in terms of limitations of our software, the biggest problem is the detection hijacking, which means that one of the true positives would get overrun by false positives. So the first type is the pixel hijacking, where you actually have a true positive, and by random chance, you also get some random noise that exceeds the threshold, and it actually has a bigger light than your real detection. You can usually detect even those that are lower than the noise by the fact that they are a bit spread out, so you can use a few more correlations to extract them. But with our method, where we're just taking the most, the one that's the brightest, then you actually lose a few to this brighter noise. And this is also most important when you're trying to do this sorting thing where you just look at the first vectors in the image stack. Another type of hijacking comes from the fact that we're doing clusters. So if you have a lot of false positives, maybe from some image artifact that is near the real detection, those will actually get you some detection vectors and will cluster. And you might have a real detection that also clusters with it. And when you're trying to find the detection in the refinement stage, you might actually get the wrong one, and it's going to be removed later on. And another type of cluster hijacking, which is pretty nasty, is something we call catastrophic percolation. So when you're going with your detection thresholds really low, then what's going to happen is that you're going to start to get detections from every pixel, and those are going to cluster, yeah? And there is a phase transition, actually, where the clustering begins, instead of increasing exponentially, or actually decreasing exponentially, it starts having a parallel distribution. And you're just going to start having very quickly very big clusters, which are going to hijack your real detections, and your real detection rate is going to just plummet to just a few detections. And that's it. Yeah, you can't go lower than that. Thankfully, we do have something in mind to fix that in the future 2 releases. And otherwise, it's just some lack of time to do all the reporting stage afterwards with better O-Cs and so on. And this is something that we are working on and increasing the automation so we can send the data as quickly as possible to MPC and publishing, for example, like this seminar here, trying to get the information out from all the stuff that we've done. Otherwise, for a longer term, to get this pipeline running, we also want to integrate more third-party tools. So what does this all mean? You know, what does having this very fast synthetic tracking mean for detecting these near-Earth objects? First, I expect on shorter term, synthetic tracking to completely overtake the blink detection method. It might sound very powerful statement, but I've seen this in our team. We're no longer using blink at all, or at least maybe just once or twice a video has fallen back to some blink where it was easier, but that's it. Once you have access to synthetic tracking, you're not going to go back to blink. And this is why I expect that even the big surveys will start seeing these so-called shallow deployments. So these big surveys have hardware designed for blink. But to get deeper than blink, you can actually just take a few more exposures. Yeah, instead of, I don't know, 2 or 3 as they're taking now, maybe take 10 or 12 or something like this. Not go for very long exposure integration times as you would, for example, with a small telescope. And this gives you a lot more depth to your research, and you don't need to have dedicated hardware, which are probably gonna happen with some dedicated survey proposals, again, in the near term, but the implementation is gonna take a bit more time. Also, expect more and more knowledge to be disseminated about this method, again, on short notice. And this will probably lead to even more developments around this area. So what we expect in long term is that this method will morph a bit, maybe taking a few of the blink ideas to be able to more effectively work on very long integration times, maybe even beating the diurnal cycle, observing over multiple nights. I'm thinking here, for example, the famous SOAR paper. And I expect, again, going further, all the big surveys to be synthetic tracking. The thing is, this synthetic tracking will just allow you to go deeper at the same mirror size. So this is what really happens here. And there are a few more advantages in that you can use some less common instrumentation like telescopes in space or on balloons, where you're limited by the size of the mirror and the time you can expose. And yeah, that's about it. If there's any questions. Yes, Ovidio.
Thank you. Please show up on the internet if you can access internet. Euronear page, discoveries, and comment a bit on the pictures, on the animations to underline our discoveries.
Okay. Well, I can try to show it, but I'm not sure if I'm the right person to do this. I think you would be the best person to show this, but sure. So if I'm going on this page, it might take a bit of time to go through all this. Yeah.
Discoveries, and the last ones either discovered,
yeah,
ParaSOL, yeah, any of them, click on them and show them the animation.
Maybe this one. Not sure why they're loading so slowly.
Fine, so using the CASI, which is a 1.6 meter South Korean telescope in Chile, we've discovered a few trailed, quite faint near-Earth asteroids recently. So this is one of them.
Yeah, this is another. What I'm not seeing is that really fast one, 2024 CW2 actually on your page. But yeah.
This is another trailed.
This is actually through TICO. Not all of them were actually discoveries too, but yeah.
And one is very faint, above, clearly above the blinking method.
Yeah. Okay. Do you want me to show anything else, or what's?
The two last lost asteroids.
Oh, these ones. Okay.
Exactly. which were unfortunately lost because of lack of telescopes to recover them. Was also very faint and trailing, missed by major surveys and other blinking detectors. And another one.
Loads.
Yeah, so these are a few achievements of our ParaSOL project, where you, Malin, have developed, you've been the main developer of the software, which comprised a team of professionals and amateur astronomers like you, but very good software developers, whom we involved in the project, in this Romanian project, basically. Thank you.
Hi, Malin. Thank you for the presentation. I really like your work. I have several questions, but I think I'm going to just ask you one. So what's the proportion of false positives against true positives, and how do you deal with them?
So if I remember correctly, the numbers I have best in mind are from this CASI telescope where we did a bit of a tuning of STU. And thing is, you can go lower and increase the number of false positives, but then your reducer is going to have a hard time. And we've decided, based on the size of the CCD, to go to 16% true positives. So it all depends on how deep you want to go. But for example, what we did with CASI was at 16% true positive rate.
Okay, that's really good. Do you have any automatic method to filter them up?
To some degree, yes. And for example, we can use the shape of the object for very long ones that don't move very fast, or they are, let's say, long in the wrong direction compared to the motion direction. Then, yeah, we can, for example, get rid of those with these filters.
Okay, thank you.
Thank you for your presentation. So I have a more like general question. Do you think with your project you could involve the amateur astronomy community to help you with processing the data, the observation of the validation? Do you think it's feasible, or is it like too complicated to involve some amateur people in that project?
Well, we're already doing this. So we're basically professionals because we were hired for this project. So for example, I'm a software developer. Now I work at the Continental Corporation doing automated parking. But this is a project in astronomy. And this, as Javier said, I'm a bit passionate about astronomy. And I am more of an amateur astronomer by design. And we also have other people like Luci and Daniel in our team who are amateur astronomers. Yeah, we call them professionals because we pay them. This is something I've learned from Marcel. Usually the problems with involving more people is that you have to train them and they have to be available. It happened to us in the past. Ovidiu knows best that sometimes you train somebody and then after that they don't show up. But in general, we've had success with amateurs. So I would say that, yes, this works pretty well.
Okay, thank you.
More questions? No? Then let's thank again Malin for this nice presentation.
Thank you also.